This screencast is a review of valence electrons and Lewis dot diagrams, as well as instruction on bonding, ionic bonding and covalent bonding. The information contained in this screencast can be found in chapters 4 and 9 in your textbook. So quick review on valence electrons. Just recall that we determine the number of valence electrons based on the group or the column that an element is in on the periodic table. Okay, so our valence electrons can be anywhere between 1 and 8. So in the first column, all of those elements have one valence electron. So all of these elements, okay, will have one valence electron. In the second column, all of these elements have two valence electrons. Recall that we do not do anything with the valence electrons with these group D elements because they're irregular. We skip them and we continue over here to boron's group where we have 3 valence electrons. Then we have 4, 5, 6, 7, and 8 valence electrons. Also, recall that the one exception to this rule is helium. Helium is going to have 2 valence electrons, even though it's in column 8. That is because helium only contains 2 electrons, and our first ring around the nucleus holds 2 electrons, so hopefully you'll recall that from our Bohr models. All right, so how do we draw our Lewis dot diagrams? This is going to be very important in this chapter, so if you didn't learn it in the chapter on atomic structure, you need to make sure that you go back and review that screencast as well. But recall that we write the symbol for the element, and then we add the dots that represent the valence electrons. Carbon is in group 4. It has 4 valence electrons, and so that's what our Lewis dot diagram will look like. Recall that when we do this, we put our dots in one on the top, one on the right, one on the bottom, one on the left. So we have one on each side before we go back and we add a second to any side. An example of that would be chlorine. Chlorine has 7 valence electrons, so I'm going to put one on the top, the right, the bottom, the left. Now that I have my 4 electrons placed, I'm going to go back around and start adding a second one until I get to a total of 7 valence electrons. Let's say I have less than 4 valence electrons, like with aluminum. Aluminum only has 3. That's fine. We just put one on the top, one on the right, one on the bottom. You don't always have to go top, right, bottom, left. You can go in any particular order you want. Beryllium, for example, I could put one on the left and one on the right. Okay, the only exception to this rule, again, is helium. Helium, recall, has 2 valence electrons, but because those 2 electrons fill up the outer shell, we put those 2 dots beside each other for helium. Why do elements combine to form compounds? Let's take a look at table salt as our example. Table salt is composed of an atom of sodium and an atom of chlorine that have been chemically bonded to each other. Now, sodium is a soft silvery gray metal. It's highly reactive. In fact, it will react almost instantly with water. It will react almost instantly with air. And for this reason, when we have sodium samples, we store them under a mineral oil so that they don't react with anything around them. Chlorine is also highly reactive. It's a colorless, odorless gas. It's actually poisonous. Yet when they combine, they form this stable compound that's not reactive. It's a crystalline white solid called table salt. They do this because they're each more stable together than they are apart. So elements combine to form compounds because it makes them more stable. This is called the Octet Rule. Atoms want to be stable like the noble gases. Noble gases do not react at all. We say that they are inert. So to be stable, these other elements want to have a full outer energy level or a full outer shell. That means they want to have a total of 8 valence electrons. Again, this is called the Octet Rule. This is a very important rule, and you want to remember it. Atoms tend to achieve the same number of valence electrons as a noble gas, meaning they tend to end up with 8 valence electrons. The way they do this is different depending on whether they are metals or nonmetals. Recall from the previous chapter that metals are to the left of the staircase on the periodic table. Metals obey the Octet Rule by losing valence electrons. Nonmetals are to the right of the staircase on the periodic table, and they obey the Octet Rule by gaining or sharing electrons. And we'll get a little more into this here in a few slides. Also recall that when we gain or lose electrons, what we're actually doing is forming an ion. An ion is simply an atom or a group of atoms that acts as a unit and carries a charge. Here on the top, we see an example of what we call a cation. Recall that a cation is going to be an ion that has a positive charge. So here we see where sodium as an atom okay, has 11 protons and 11 electrons, giving it a net charge of 0. What happens is that the lone electron in this outer shell, this electron right here, okay, it's going to go away. And notice in our new picture that that shell is now vacant, okay? There are no electrons in this outer energy level. So we have 11 protons and 10 electrons, giving that ion a net charge of +1. But look what happened. I told you that the atoms achieve stability by having a full outer shell, by wanting to have 8 electrons in their outer shell. Sodium, by losing that one lone electron, now has an outer shell that has a total of 8 electrons. Instead of it being the third energy level, the full outer shell is now the second energy level. Also recall that when we have an atom that gains electrons or forms a negative charge, it's called an anion, and we see that here to the right. Okay, so here's our example with fluorine. An atom of fluorine has 9 protons in the nucleus and 9 electrons in the energy levels. So that gives it a net charge of 0. And we can see here in this outer energy level there's space for one more electron. What happens is that an atom that loses its electron will give that electron to the atom of fluorine, filling its outer energy shell up. For our ion, we have 9 protons in the nucleus, but we have 10 electrons outside the nucleus, giving it a net charge of -1. Again, our atom has obeyed the octet rule by filling its outer shell so that it contains a total of 8 valence electrons, and we see those here in this outer second energy level. So there are 2 basic types of bonds that an atom can form. The first is called an ionic bond. An ionic bond will form between a metal and a nonmetal. The metal, recall, forms a cation, and the cations will lose their valence electrons. The nonmetal will form an anion, and it will gain valence electrons, and we're going to show the movement of electrons using arrows. So let's look at some examples of what an ionic bond would look like. All right, so we start by drawing our Lewis dot diagram. So I have sodium, which has 1 valence electron, and I have chlorine, which has 7 valence electrons. Okay, and what I'm going to do is I'm going to show that this one lone electron from sodium wants to move over here to chlorine. And when it does that, I end up with NaCl. Now let's say I take another atom of sodium, okay, and it has its 1 valence electron, but now I'm combining it with an atom of oxygen. And recall that oxygen has 6 valence electrons. Well, sodium wants to get rid of its 1 and give it to oxygen. My problem now is that oxygen only has 7 valence electrons. I have 2 here, 2 here, 1 here, and 2 here. Oxygen has space for 1 more electron. In order to fill that space, we're going to add another atom of sodium. Okay, this electron moves in with the oxygen as well. So now I have my 2 sodiums, which have lost all of their valence electrons, and I have my oxygen, which has a total of 8 valence electrons. When I write my formula, I need to pay attention to the fact that I have 2 sodiums. So I write Na2O as my formula. Let's look at another example. Here I have an atom of magnesium. Magnesium has 2 valence electrons. If I combine the magnesium with an atom of oxygen, which recall has 6 valence electrons, then the magnesium wants to get rid of both of its electrons. It gives both of them to oxygen and ends up with the formula MgO. The final example I want to go over is as complicated as it gets, and that's when we combine magnesium with nitrogen. Okay? Magnesium still has 2 valence electrons. Nitrogen has 5. Okay? So these 2 electrons from magnesium are going to move on to nitrogen. What's the problem? That's right, I've got this one lone electron all by itself down here with nitrogen, and it needs to be paired up with another electron. That means I need to add another magnesium to the mix. Okay, I do that, and this electron moves over to the nitrogen, But now my problem is that I have this extra electron on the magnesium that I need to get rid of. I'm going to go back, and this time I'm going to add another nitrogen. Okay, this nitrogen gives me a place to move that electron, but I'm left with 2 empty spaces on this nitrogen that I need to fill. One more magnesium will solve my problem. These 2 electrons move over to nitrogen, and now all of my metals have lost all of their electrons, and all of my nonmetals have a total of 8. What's my formula going to be? It's Mg3N2. In contrast, covalent bonding occurs between 2 nonmetals, and this is going to be when the electrons are shared. So in ionic bonding, electrons were gained or lost, while in covalent bonding, both atoms say they share common electrons. We're going to show how the electrons are shared with circles, and we're going to have special bonds in this case. They're called single bonds, double bonds, and triple bonds, and I will show you examples of each. Okay, so let's take a look at phosphorus. Phosphorus is a nonmetal that has a total of 5 valence electrons. If phosphorus were going to combine with chlorine, which has 7 valence electrons, we see that phosphorus needs to gain 3 electrons and chlorine needs to gain 1 electron, and neither one wants to give up any of its electrons. So what they do is they share their electrons. So what's circled here will be claimed by both atoms. So this chlorine now says it has 2, 4, 6, 7, and 8 electrons, while this phosphorus says it has 2, 3, 4, 5, and 6 electrons. That's great, but the problem is that each atom needs to have a total of 8 electrons. So what we're going to do is add another chlorine, which will also have 7 valence electrons that can be shared with the phosphorus. Again, 2 electrons are shared between the atom, which is fine for the chlorine, but phosphorus still needs 1 more electron. It gains this electron with the addition of 1 more chlorine atom. Now we see that both atoms are full with a total of 8 valence electrons. Our formula here is PCl3. Notice that the only electrons that were shared were the ones that were single electrons. The electrons that are already paired up do not participate in sharing in a covalent bond. Let's look at the example of carbon combining with oxygen. Recall that carbon has 4 valence electrons, and oxygen has 6 valence electrons. Carbon will share an electron with oxygen, and it will share a second electron with oxygen. This is called a double bond because 2 pair of electrons are being shared at the same time. Notice, though, that carbon now has a total of 6 valence electrons, not the 8 that it requires. So that means we need to add another oxygen. When we do this, we see that carbon can share 2 more pair of electrons to fill its outer shell. So I now have oxygen double bonded to carbon 2 times. My formula is CO2. Another example of a covalent bond is when carbon combines with hydrogen. Hydrogen, like helium, only needs 2 electrons in its outer shell to be stable, so it achieves it by sharing its electron with carbon. That fills out hydrogen's shell, but it leaves carbon needing 4 more electrons. That means we need 3 more hydrogens to fill out carbon's outer shell. If we were to draw the stick structure for this, everywhere we see a circle, we would draw a line. So we would have hydrogen, single bonded to carbon, single bonded to hydrogen, and our formula is CH4, which is the formula for methane. When nitrogen combines with another atom of nitrogen, we have an example of a triple bond. Each nitrogen atom has a total of 5 valence electrons. That means that they each need to share their single electrons, all 3 of them, in order to both be full. Okay, drawn in a stick diagram, this would be N, nitrogen, triple bonded to another nitrogen. Okay, again, right here is a triple bond, and it's called a triple bond because it's 3 pairs of electrons that are bonded together. Our formula here is N2. Try these 6 practice problems. Start by drawing the Lewis dot diagrams for each element listed. If the atoms listed are a metal and a nonmetal, draw arrows to show the movement of electrons. If the elements listed are 2 nonmetals, draw circles to show how the electrons are shared. Don't forget to write the formula for your compound at the end of your notes. Do all 6 problems, take a picture of your work, and upload it to Schoology.